Welcome. Today we'll be talking about electric field. Electric field or vector E with a direction and a magnitude as well. So if you remember, a charged particle can have its own direction of electric field. We have two kinds of charges, positive and negative. We have positive charges, we have outward electric field, and the negative should have an inward direction. If we all remember, we have here a positive charge. The positive charge, the field of that is going outwards, and if I were to pick just a point here, let's say, call it position P, the field at that point would look like this. And as you can see, it is a tangent line. So this is what we call vector E, P. Now the direction of the electric field at any point is tangent to the field line through that point. Next, let's talk about electric dipole. Now, electric dipole, from the word itself, dipole, we have here di means two and pole means polarity. What does that mean? Let's have an example. Here's my H2O, my O being really electronegative compared to my H. Might as well redraw this. H and then H. Okay. Now, if I were to look at this, they've got different polarities. They've got different polarities. I must have partially positive, and this should be partially negative. If that's the case, looking at it, I know that the electronegativity increases from your H to our O. So this is a trend of our electronegativity. On the other hand, we'll be defining another variable. It is called electric dipole moment. The electric dipole moment is from negative to positive. Electric dipole moment, denoted as your P, with a direction, is always from negative to positive. If that's the case, if you were asked what is the electric dipole moment of the molecule or of H2 in this case, then that should be from your O to your H, which is from negative to your positive. Alright, so let's talk about torque, electric potential energy, force, and your dipole moment. Since we have torque here, we already know that torque, if we care to remember that torque can have direction, can also have magnitude. If that's the case, then you can have a vector torque and you can have a magnitude torque. Electric potential energy can also be put here. Our force as well, and then our P here can have direction and can also have magnitude alone. So it can be in case of dipole moment and our torque, they can be answered in two different ways. You can include the direction, or you can just have the magnitude. Most likely, they're asked, and if they're asked, they want, or the people asking, they want the direction and also the magnitude. Let's talk about the very important formula that you must remember, rather. Now, for our torque, I'll be starting with our vector here. Torque is equal to our dipole moment, electric dipole moment, cross E. So if it is a cross and the vector product, then we need sine. That would mean we need torque, PE, sine, and the angle phi here. This is for with the direction, and this is for the magnitude. Now, what about our electric dipole moment? Our electric dipole moment, the magnitude is only P is equal to Q D. The Q is the intrinsic charge of our charge, so it is not 2 coulombs or 3 microcoulombs. This is 1.6, the intrinsic value of the charge. Now, if we need the vector of our P, then we're only looking for the direction, and for us to see the direction, we can have we can have it based on our free body diagram. So this is from our free body diagram. Next, for our electric potential energy, we have our dot product. So that would mean electric potential energy is equal to negative electric dipole moment dot E. If we'd like to have the magnitude, that would be U negative PE. Because this is a dot product and not a cross product, you will need to have a cosine phi. If that's the case, then looking at the vector and when getting the magnitude, you can find a way. You can find a way memorizing the formulas quite quickly. If it is cross product, then you need sine. If it is a dot product, you need cosine. Right. And for the force here, this is just by definition that if you have a uniform electric field, then the force on the two charges, if you've got a given dipole, must be equal and must be opposite. Why is that? Well, a dipole, from the word pole and from the prefix di, you've got two charges with the same magnitude but different signs or opposite charges. Let's have a quick example pertaining to force and torque on an electric dipole. So imagine I've got here uniform electric field. Our uniform electric field is with vector E. Now, the uniform electric field, I've got a dipole. Let's say this is my positive charge and my negative charge. Let's assume that they've got the same magnitude or equal, rather. But then you can see that they've got opposite charges. Now, if this is my negative, then this is my negative Q, and this is my positive Q. If that is the case, then I can say that this is a dipole. What is being asked here is we've got to find the net force exerted by the field on the dipole. What is the net force of net exerted by the uniform electric field on the dipole? So F net by E on dipole. As we said a while ago, by definition, if you've got a dipole and well, not really because you've got a dipole, but because you've got a uniform electric field, then the forces on the two charges must be equal and opposite. If that's the case, then the total force on the dipole by the electric field must be zero. Just make sure that you know what zero Newton. For letter B, we're asked for the magnitude and direction of the electric dipole moment. So we need the magnitude and the direction of our electric dipole moment. First things first, let's have a free body diagram. For our free body diagram, we need three things. We've got to have our torque, we've got to have our electric dipole moment, and we've got to have our electric field. All of these things showing us direction, so they must have vector signs. Now, looking at the two charges, they are unrelated by the looks of them, but then I can connect them so that we have an axis given. And from the definition torque, this is the force that makes the system rotate. So I'd assume that this is where torque is. I'll be drawing torque as a dot here for our free body diagram, naming it T or tau. And our E here, because I've got to have my E, would be the one going to the right, because electric field here is from left to the right. And this is my electric field. And if we look at the charges, we defined electric dipole moment in terms of the direction being from negative to positive. So if that's the case, then the electric dipole moment is actually this. Then it would look quite similar to my free body diagram that I'm showing you right now. So our free body diagram consists of three things: our tau, our P, electric dipole moment, and our electric field. If this one's given to be as, let's have another line here. Right, now if this is given to be as your 35 degree angle, and you see that this 35-degree angle is absent here, we don't see anything there. What we see here is the opposite. It's this one. So from being a straight line, you've got 35, and straight line is 180. Then that would be 180 degrees minus 35 degrees. Then that would be 145 degrees. What we're looking at right now is 145-degree angle. So this is 145-degree angle. Now, why is that important? That's important because we've got sine phi and cosine phi. We'll be dealing with the phi's later. Phi, P-H-I, phi. Right, so going back to our electric dipole moment, we have here P. We said P is only P equals Q, due with the intrinsic value of our charge. Now your Q is 1.6 times 10 raised to negative 19 coulombs, and D is your distance. Excuse me, I forgot to tell you that the magnitude for your distance and your electric field is given to be R is equal to 0.125 nanometer, and the magnitude for your electric field is 5.0 times 10 raised to number 5, yeah, N over C. Right, and given that, we've got here our D, which is 0.125 times 10 raised to negative 9 m. Get the answer here. For the direction, because we need the direction of our electric dipole moment, we can simply say it's from negative to positive. It's from negative to positive charge, and if you'd like to make use of the angle, we can also say that it's from negative to positive charge and 145 degrees clockwise from the electric field direction. It's supposed to be clockwise. As we can see here, this line here, this axis, would serve as our axis when it is rotating. So in this case, it's going to be 145 degrees clockwise. Although you can just say it's going to be negative to positive. That will do as well. So here for our direction, negative to positive, or 145 degrees clockwise. Right, now for letter C, we've got to know the magnitude of our torque. Magnitude and direction of our torque. Now I'll have tau, and I also have vector tau here. For vector tau, we need vector is equal to our P cross E. Then that would look like PE sine phi. Now for P sine phi, that's for the magnitude, we'll have P given, well, not given, but from our answer a while ago, times our E, which is said to be 5 to the 5th. 5 times 10 raised to the 5th, N over C. Sine phi here is 145 degrees. So the answer must be Newton meter. In Newton meter. Newton meter. For the direction of our torque, we need to use our right hand rule. But if you're having trouble or you're not very confident with your right hand rule, you can just see if your magnitude is positive, then your torque must be anti-clockwise. But if your torque is negative, then your torque must be clockwise. If that's the case, I know that the answer is positive, then I know that the rotation of our torque is anti-clockwise. And we can use that logic when we're not very confident using or doing the right hand rule. Now lastly, we've got our D. Our D is, what is the potential energy of the system? And the potential energy of the system is given to be as negative PE cosine phi. Our negative P can be, from our answer a while ago, our E is 5 to the 5th again, cosine phi. Our phi is still 145 degrees. Now, this thing will be negative, but then because of our cosine for 145, then we've got to have a positive answer for our electric potential energy. So, the answer here must be positive. Again, I'll be giving the answers by the end of the video, so stay tuned. Now, for our electric potential energy, we've got to have joules. This is in Nm. This one is in Cm. Our torque is, yes, Nm.